don't think I ever lived
Let's
line in C, which is R2.
So our second class of the afternoon, we're happy to have Josh Zahl from BBC, who will talk about cutting curves into little pieces.
Thank you. Thank you for the invitation. I'm actually going to start with a quiz for the people in the back. What's the largest number that you can see? Four. Okay, thank you. Perfect. Okay, thanks. Yeah, so we're going to talk about cutting curves, and actually just a little bit of disambiguation. So Andrew spoke a little bit about cutting, or mentioned the word cutting, and the ideas in Andrew's talk are going to also play a role in mine. But when I use the word cutting, I have a different meaning of the word. So those will be separate. Okay. So I'm going to talk, well, so I guess the overall name of this week is Algebraic Methods in Combinatorics. And I realized what I'm actually going to talk about is not so algebraic, but I was trying to have the idea of a method where I'm going to describe a technique which can be used to prove a few results that I'm aware of, but I have a hope that maybe it can prove more results that haven't yet been done, and maybe this technique itself will be of interest to you. So I'll talk about a few final theorems, but I think the theorems are less interesting than the ideas that we use to prove them. So that's at least my hope. So as far as I'm aware, this technique is used to prove results in incidence geometry. And so maybe everyone in this room knows what incidence geometry is, but the basic question that people in incidence geometry ask is, it's an area of extremal combinatorics where you have a certain collection of points and a certain collection of objects, which in this talk are going to be algebraic varieties. So you can think curves in the plane or surfaces in R3, and you fix the number of points and you fix the number of varieties and you move them around to maximize the number of incidences, which is when a point is on one of the varieties. And the question is, how many incidences can you achieve as a function of the number of points and the number of varieties that you can fix? Okay, so the really the birth of this field was this question asked by Erdős and answered by Zemredy and Trotter, which is if you have m points, if you'll write it, Zemredy and Trotter theorem. So if you have P, which is a set of m points in the plane, and a set L, which is a set of n lines in the plane, they bounded the number of incidences that could occur. They said the number of incidences between this set of points and this set of lines is up to constants at most m to the 2/3 times n to the 2/3 plus m plus n. So maybe everyone in this room already knows this, but just keep in mind, right? So you're fixing the number of points, you're fixing the number of lines. I hand these things to you, you have to move them around. 2 points can't be on top of each other, similarly for 2 lines. Other than that, you're trying to maximize the number of incidences. This is the number you can achieve, and this is sharp. Okay, so that's known. This is sort of one of the very few results in incidence geometry where we actually have a sharp bound. And maybe you all know the proof of it, but I'm going to quickly sketch a proof. It's going to be useful later on. And so this was proved in, I believe, 83 by Zemredy and Trotter, but the proof I'm going to sketch is a much more modern one, so sort of a retroactive view of history. And the major technique that's going to be used to prove this is the discrete polynomial partitioning theorem of Guth and Katz. That was a major ingredient in their proof of the distinct distances problem, 2010. I'm just going to look at a few special cases of that. And the basic idea is the following. So I have my collection of points which are placed on the plane by some adversary in a way to create as many incidences as possible. And it's also a bunch of lines. And what I'm going to do is I'm going to find a polynomial of degree d, which partitions the plane by taking away the 0 set of that polynomial into roughly d squared pieces. So they find a polynomial. D is the parameter that I get to choose, so that the plane take away the 0 set, let's call this polynomial P, take away the 0 set of P is a union of roughly, I'll even say approximately, d d squared open connected sets, which I'm going to call cells. And there are at most, so there are m points total, there's d squared cells. If the points were distributed evenly throughout the cells, there'd be roughly m over d squared points in each one. So I'll say at most m over d squared points per cell. So the points are very well distributed. You could imagine the zero set looking something like this. Though it's not going to be the case that the lines, so each point only resides inside of one cell. It could be there's some points on the zero set, but I'm going to gloss over that detail. It's not going to be so relevant for this talk. It's not going to be the case that each line only belongs to one cell. A line can belong to a few cells, but you can ask how many cells can a line belong to, and every time a line enters a cell, it has to cross the zero set of that polynomial. And how many times can a line cross the zero set of a polynomial of degree d? Well, it's at most d plus 1. So if you were to look inside of all the cells, let's call those cells omega, and we sum over omega, and I say number of lines intersecting omega, this is at most up to some constant, which I'm going to ignore, the number of lines total, n times d, which is the degree of the polynomial. Okay, so this is nothing I'm saying so far as new, this is all known, certainly as far back as 2010. And now what I want to do is I want to count the number of incidences. So let's look inside of a cell. Let's look at an incidence. And you could say, well, it could be the case that on this particular line, in this particular cell, at this point, this is the only point which is incident to this line inside of that cell. And if that's the case, then I'm counting that. And how many times can that occur? Well, the number of times that a line enters a cell, that's at most d times n. So this, what I've just described to you, where a point is incident to a line, and that's the only incidence occurring on that line in that region, that's at most d times n. The other possibility would be that there are at least 2 points on this line in that region, and I can overcount that by counting the number of pairs of points which are in a cell, because certainly that pair is being counted, so if I just count all possible pairs, I've overcounted that possibility as well. So I can say that the number of incidences is at most, well, how many cells are there? There's at most d squared cells. How many points are there in each cell? There's m over d squared of them, and when I count all pairs, I square that. So that's counted the situation here where there's 2 points on a common line in a cell. Or you could have a situation where there's only one, and that's going to be that sum d times n. And you could rearrange this and optimize in d, and you're going to get that this is at most m to the 2/3, n to the 2/3 plus m plus n. So m doesn't quite come out of this. There's another situation which I'm very much glossing over, which is there could be points which lie on the zero set of this polynomial. There could even be lines which are contained entirely inside of the zero set. And when you're really doing this, you have to analyze those situations, and m comes out when you do that analysis. But I'm going to gloss over that. That's not going to be so important. What we're going to say today. Okay, so this has been done. And you can ask sort of what were the ingredients of this proof. There were a few of them. And so one was this key fact that if I, that it was enough to count pairs of points, and that once I fix a pair of points, I've understood the line that those pair of points specify. And we have a word for this. We say that the family of lines has 2 degrees of freedom. So if I fix 2 points, in this case there's only one line that passes between both of them. I could have had that there's at most 10 lines that pass between both. So Joseph this morning was talking about the unit distance problem, where instead of points and lines, you can think of that as points and unit circles. And then if I fix 2 points, there can actually be 2 unit circles that pass through both. But 2 unit circles is effectively the same as 1 line, the way this problem works, and this same bound gives you the same result for that. Okay, so that was one piece. That when I fix 2 points, there's almost 1 line, or a bounded number of lines that pass between them. And then the other was this rather algebraic statement, where you look at each line and ask how many times does it cross the zero set, and we have a bound of that, d times n. Okay, so that's memory car, and that's well understood. And you could ask, what about trying to get new incidence theorems for different classes of curves instead of lines? And the sort of easiest to understand situation past lines, or past unit circles, which we understand as well, might be arbitrary circles. So for arbitrary circles, it's not the case that if I fix 2 points, there's at most one, or even a bounded number of circles that pass between them. There's a very large number. It is true that if you fix 3 points, then there's at most one circle that passes between them. And so you can run this sort of argument that you're counting triples instead of pairs, and you can do this whole thing, and you'll get an answer like this, but different exponents come out. And so this was actually done well before 2010 for algebraic curves. This goes all the way back, I believe, to the late 80s. I'll erase this over here. But the sort of canonical form, which is the most general one we know, is due to Pock and Scherer. So I'll just say that. Theorem of Pock and Scherer from, boy, 98. And what they say is if you have m points and you have n curves, so they actually prove something fairly general. Their situation, they don't have to have algebraic curves. They have to do it in a more general topological setting. I'll say you have m points and you have n curves. And the curves have what's called k degrees of freedom. So colloquially what that means is if I fix k points, there's at most a bounded number of curves that pass through all k. Then the number of incidences is big O m to the k over 2k minus 1, n to the 2k minus 2 over 2k minus 1, plus m plus n. So if k is 2, which corresponds to lines, then you get back the majority product. So this is a general technique that has been known for a while for proving incidence theorems, where you say, okay, I no longer have the case that when I fix 2 points, there's at most one line or one curve that goes between both of them, but when I fix k of them, there's roughly 1, and I can run that perfectly. So there was another idea, which is quite a different one, which is called cuttings, or at least that's a name that's given to it. And this also goes back to roughly 98. And this was an idea by Tamaki and Tokuyama. And I'll write down what they did. At least I'll draw a picture of it. So you can imagine I have a collection of circles. These are not unit circles, they're arbitrary circles. And what makes this collection bad from trying to run the argument I just wrote on the board a few moments back is I might have 2 points, and there might actually be a large number of circles that pass through both those points. And in order to uniquely specify a circle, I actually have to fix 3 points. So they said, well, what if instead of considering circles as these entire objects, I were to take my pair of scissors and start cutting these curves into little pieces. So they're going to make some number of cuts, and after they've done that, they no longer have circles, but they still have some nice arcs that are pretty easy to understand. And they're going to make these cuts in such a way that after the cuts have been made, when I fix 2 points, there's only one arc that passes between both of them. And then you can try to run an argument similar to the previous one. So you can always do this if you're really inefficient. Just whenever 2 curves cross, you just chop them. And then if there's n curves, there's roughly n choose 2 places where they cross, or maybe twice that, and you get roughly n squared cuts. And when you try to run this argument, it's horribly inefficient. So the name of the game is to try to take these curves and cut it into as few segments as possible, so that after you've done this, no two curves intersect in 2 places. Right? So this is the sort of situation. After you're done cutting, you never want to see something that looks like this. Okay. So there's a definition, which is that a collection of curves are called segments if no pair of them intersect in 2 places. So in the same way that line segments have that property.
The cutting has to be continuous, or can you take these 2 parts and these 2 parts as two curves?
So what we're doing is, each one of these, to make this picture less busy, I take a circle and I remove a finite set of points, and each of the connected components is now a curve in its own right.
Why does it have to be? It has to be connected. That was the question.
Oh, yeah, they have to be connected. So I'm looking at the connected components that are obtained after I do this cutting. And it being connected ends up, for a lot of these groups, actually being important, because there is a topological flavor to what's going on. For exactly the same reason that earlier argument I had of this d times n had to do, there was some topology involved, so connectedness is important. Okay, so I'll say set C, Cal C of curves is called a family of segments. segments is the keyword here, if no pair of curves intersect twice. And you could ask what's a curve, and so it doesn't, any reasonable definition in your head is fine, but to be concrete, we could say these are simple open curves. These are the homomorphic images of the interval 0, 1. So like a circular arc would be fine. If you were to have a circle, that's in this definition not a curve, but you can cut it into two, and that's a pretty harmless operation. And now you have these open segments. Okay, so what Maki and Tokiyama proved, I'll write down their names first of all. So this is Maki. Is if you have n circles in the plane, you can cut them into roughly n to the 5/3, maybe plus epsilon, I'm not sure, segments. Okay, so the trivial bound would be n squared. They got an improvement over that. And this was improved, this was in 98. This was improved by Arnov and Scherer in 2000. They brought this exponent down. And they improved this to O of n to the 3/2 plus epsilon segments. Okay, so this result had many applications, but one application that is interesting or the most directly relevant to incidence geometry is it gives you a new bound on the number of incidences between points and circles in the plane. And what it tells you is that m points and n circles in R2 have big O of, and now I'm going to give you a function of m and n, which I claim is going to be smaller than that one over there, when k is equal to 3, which is the number corresponding to the circles. So it's going to be m to the 6/11, n to the 9/11, plus m to the 2/3, n to the 2/3, plus m plus n. And they lose an epsilon. You can kind of put it wherever you want. Let's say right here. So when k is equal to 3, yeah.
Oh, sorry, I missed it. Are these 3/2 optimal? Are they Arnold Scherer?
Short answer is I don't know. I'm not aware of any examples showing it's optimal. My guess is it's not, but I'm not sure about that. There are some related problems, slightly more general ones, where that is optimal, which makes it look like it's hard to prove this, but I'm not aware of any examples showing it's optimal. Yeah.
Are these epsilons really are they logs or they're really epsilons?
Good question. So, Boris is in the audience, he can tell me if in this particular result it's an epsilon. I think this got improved to something like log n to the, I'm going to make up a number, something like 2/7. So this may have been in a later result in 2000, I'm not positive, but something like this is what's here. So just to have in our head, circles, I haven't quite rigorously defined 3 degrees of freedom, but circles intuitively have the property that if I fix 3 points, there's at most one circle that goes through all 3 of them. So if k equals 3, and this is big O of m to the, this is 2k minus 1, so this is 3/5, n to the 4/5, plus m plus n, and you stare at this exponent, and you stare at that exponent, and it's not entirely obvious which one is better, but if you stare at it long enough, this is an improvement over that result. So this idea that you're cutting these curves into pieces is genuinely doing something better than what's happening over here. But just staring at this ability to cut a bunch of circles into segments, it's not entirely obvious how these exponents pop out. So I'll just sketch very briefly what goes on. So their original improvement is different from what I'm going to do.
To compare them, the typical cases are equals n or?
That is certainly an interesting case to compare. compare. And if you were to put in m equals n and just compute the exponents that come out, you will discover that this one is better. And so that tells you that there is at least one range of parameters where this is better. What you'll discover is that aside from this epsilon, which we can sort of ignore, that this one is better than that one everywhere except where you're in a trivial range where it's just the m's or the n's dominate. So this one really strictly dominates that one everywhere in the interesting range of parameters. Which, I mean, is not a particularly, you can do the algebra. I don't think there's that much insight to be gained from doing the algebra, but you certainly could. Okay, so the question I want to answer is, how do you take the ability to take a bunch of curves and cut them into segments and turn it into a incidence bound? And we can go back to the things that I erased, this proof that we had a moment back.
Just before you erase.
Yeah.
Are these theorems truly about circles, or if I said I have a bunch of curves and all I know is there's 3 degrees of freedom and I want to, so to speak, reduce the 2 degrees of freedom by cutting into segments, is there a non-trivial?
Yeah, so you're foreshadowing what I'm going to talk about in just a few minutes. So if
Oh, okay.
maybe save that question, and if you're still not satisfied with what I'm going to say, then
Okay.
you can ask it again. Okay. So we can do the same thing as before, where we have this conditioning polynomial. So R2 minus C of T is a set of d squared cells, and there are still roughly big O of m over d squared points in each cell. And so that hasn't changed because the points know nothing about the curves. And now we can ask this question, and this is going to be really crucial, if you were to sum over all the cells and ask for the number of segments intersecting omega, right? So I took this collection of n curves, and I took my scissors and I cut them into a bunch of segments. I cut it overall into n to the 3/2 segments. Maybe here's the numerology. We have n circles. We have capital N, which is little n to the 3/2 plus epsilon segments. And now I take my polynomial, and which maybe looks something like this. And I look inside of each cell and I ask how many segments are inside of that cell. And we can count that, right? Because if I have a segment which is inside of a cell, either the curve, the circle that it's a part of, is crossing the boundary of the polynomial, and that can happen for each circle at most d times, or the segment lives entirely inside of the cell, and this actually gets back to your question about connectedness, because there's really a topological thing going on here. And so the answer is d times n plus capital N, which is the number of segments. Okay, so hopefully that's clear why this is. If not, please ask. And what comes out of this, when you then run Zimmer-de-Trotter, that same argument, which I was claiming for lines, but really I'm just using the fact that when I fix 2 points, there's one segment between them, I get that the number of incidences between m points and n algebraic curves that can be cut into capital N segments is big O of m to the 2/3, n to the 2/3, plus m plus capital N. So Jordan, maybe this gets back to your question a bit. The implicit constant here is going to depend on the degree of the algebraic curves, because in front of this d is an implicit constant, which is the degree of the curves. Okay, so nothing I've said here so far is new, right? I mean, all this, even though there's some sort of revisionist view of history with some new techniques, this all goes back to as far as 2000 that this was all known. And so then the final question would be, how do you, so this is true, and in our world, capital N is little n to the 3/2. So this is now an incidence theorem. It's not quite the incidence theorem we have over here, but I'm going to say that we can take our arrangement of points and circles and divide it into a bunch of subproblems. apply this argument to each of those subproblems and recover this bound here. And then that's a fairly well understood process, which I won't go into, but I'll just say that we know how to do that, and there's nothing new going on there. And so this was the state of affairs in roughly 2000 or so, or maybe 2002. And the question could now be, what if we want to apply these sorts of ideas beyond circles, but to other classes of curves? And that's where things got a little tricky.
Josh?
Yeah.
I just wanted to comment that the middle statement you made doesn't require algebraicity at all.
You are absolutely right. This middle statement does not require algebraicity. You can run the normal proof using the crossing inequality.
Since someone asked the question about algebraicity.
Oh, that is very true, yes. So I am, again, foreshadowing where I want to go, where similar statements like this are true in higher dimensions, where we don't know how to do it in any setting other than algebraicity. You're right that in the plane, instead of using this proof I just sketched of Zahl Trotter, we could have used the one using crossing inequality, and this would work as well. Yeah. Thank you for that. Cool. Okay, one second. So you can imagine, we still live in the plane, and we want to have improved bounds for points and incidences, not just beyond the Paul-Scherrer one, which is right here, but not just for circles, but for broader classes of curves. And in fact, these ideas of Arnaud and Scherrer, they work not only for circles, but for pseudo-parabolas. So these are families of curves where any two of them intersect in at most two places. But you can ask for a similar thing for higher degree curves. And you can ask for pseudo-cubics, where any family intersects in at most three places. You can still try to cut them into some number of segments to make this work. But in this very general setting, of a topological setting, where I just ask that I have a bunch of curves and any pair of them intersect in at most three places, there's really no hope in trying to get a bound of this form. And the reason is I can draw a picture like this. So I'm going to draw for you, let's make sure I get the lines. Yeah. I'm going to draw for you a family of n curves where any pair of them intersect in at most three places, and you have no hope of cutting them into anything less than the quadratic number of segments. And the curves look something like this. So they're very complicated in some sense of the word. They have a lot of wiggles, and as my picture becomes more complicated, there's going to be more and more wiggles. But you can double check that this curve only intersects this curve in three places. This is true for all of these. I'm going to draw another one. So on and so forth. You can imagine a big picture that looks like this going off in all directions to n. But look at any pair of curves, any pair only intersect in three places. So from a topological counting point of view, these curves don't interact with each other in any complicated way. And yet, if you wanted to cut them into segments, you'd be in big trouble, because every pair of points like this is a witness to these two curves failing to form a segment. So I'd have to cut either here or here, and I'd have to cut either here or here, and I have n of these curves and n of these curves, and I have to cut at least n squared places. So the topological methods used to do these sorts of cuttings aren't going to work for more general classes of curves, because they can't distinguish that this is a bad situation. That's not how we're supposed to be ruling it. Cool. So I want to talk about a new result, which is some joint work of Nicholas Scherrer and myself. And what we're able to do is we're able to cut algebraic curves into n to the 3/2 plus epsilon segments, where the number of segments involves some multiplicative constant, which depends on the degree of the curves. So in this sort of situation, you could realize this using algebraic curves. The degree is going to start blowing up. So that's how we avoid this sort of problem. So this is the theorem. Zahl. It says that n algebraic curves in the plane can be cut into big O of n to the 3/2 epsilon segments. Where this big O, well, it depends on two things. So first of all, it's going to depend on epsilon, and it's also going to depend on the degree of the algebraic curves. So this picture right here is not a counterexample to this. So my hope is that this theorem, or maybe its proof, might be of interest to people who do incidence geometry. And I could just briefly say how this theorem then gives you a better result in incidence geometry for points and curves in the plane. And so this immediately, what I was saying before, gives you an incidence bound, which says that m points and n algebraic curves have a big O of m to the 2/3, n to the 2/3, plus m plus n to the 3/2 plus epsilon incidences. And in the same way that you could turn this result for circles into a incidence bound for points and circles, which was better than the previous bound of Pop and Schreier, you can turn this bound here into an incidence bound for points and algebraic curves, which was better than the corresponding Pop and Schreier bound. There's one asterisk beside the word better, which is that the original bound of Pop and Schreier was a statement about topological curves, and it asked that the curves have k degrees of freedom, which means that whenever I fix k points, there's at most bound number of curves that pass between all of them. We need a slightly different definition of what it means to have k degrees of freedom, which intuitively is capturing the same idea, and for any concrete example you might write down, it is the same number, but we define k algebraic degrees of freedom, which essentially means that the curves live in a parameter space of dimension k, which is effectively the same thing.
So Josh?
Yeah.
The implicit dependence on the degree, is it just in the end of the 3/2? Like where is it in there?
It is, no, it's not just the end of the 3/2, because, so the end of the 3/2, so it comes from a few places. So first of all, when I have n algebraic curves, I want to cut it into n to the 3/2 segments, and that number, it depends on the degree of the curves.
So should we think of the maximum degree as being fixed and then going to infinity?
Absolutely, yeah. In fact, we could even say curves. So this is, so maybe I should have mentioned that. These are the range of parameters that I'm interested in doing sorts of extreme geometry problems. So I should say n points and L algebraic curves of degree. I won't use capital D, I'll say it was little d. And to be really pedantic, this is O of d epsilon. Yeah, so that occurs, oh, we'll get into definition, but in this 3/2, but then also it occurs in this part here, because you might remember the original part of the proof. I asked how many times can a curve intersect the zero set as polynomial, and it's popping up there as well, but in a very mild way. Yeah.
Is the epsilon necessary?
Great question. Probably not. And there's sort of one point where a method that Victor and I had is not efficient, and probably doing that better would remove the epsilon. But it's not even obvious that this isn't even correct at this moment. So,
What are the worst examples?
what are the worst?
For the exponent? Look at
Well, I don't even know if the
what do you know about the exponent? How small could it be? For the cutting, for the
Yeah.
cutting term.
Yeah, so I don't know. So we reduce the cutting, this question of cutting curves to a different problem, which I'll sketch briefly. And if you tweak that different problem slightly, then 3/2 will be needed. But I don't know what this exponent needs to be. I think you could show without much difficulty. I'm really not sure is what this exponent should be. I think that's an interesting question. If you can improve this exponent, you would end up improving this bounds.
So the epsilon is, there exists an epsilon such as this true, or is it?
No, it's for every, yes, that's a good question, so I apologize. What this notation means is for every positive epsilon, there exists a constant which depends on both d and epsilon, so that the number of incidences is at most this particular constant times this to that fixed power of epsilon. Yeah,
It's
so that-
equivalent with writing epsilons plus the whole one.
that would be the, yes, yeah, that's a different notation. And, okay, so, maybe in the interest of time, I'll just state a result, which I think shouldn't really be the focus of this talk, and I hope that the focus is more on the methods, but at least to prove that the methods can do something, there is a theorem of Schreier itself, which says that if you have m points and n curves, let's say algebraic curves, and to put them in the same framework over there, we'll say they have degree less than or equal to d, and they have k, what I'll call algebraic degrees of freedom. So this is meant to mirror the idea of having k degrees of freedom. Maybe I'll say i.e. they live in a k-dimensional parameter space. Then the number of incidences is at most, and now I'm going to write down some function of m and n, which is better than the bound I wrote down earlier due to Schreier. Staring at it, it's not obvious that it's better, but you'll just take my word for it that it is. So it depends on d, and I'm going to lose an epsilon, and it also depends on an implicit constant that I sort of buried in this definition of what it means to have k algebraic degrees of freedom. So I'm saying they live in this k-dimensional parameter space. So parameter space is itself some algebraic variety in the overall space of degree d curves. And that algebraic variety itself has some degree, which is describing how complicated this parameter space is. And as that gets more complicated, of course, this bound is getting worse. But we imagine fixing the parameter space and then taking a larger and larger number of curves from that parameter space. Anyways, what comes out is something like 2k over 5k minus 4 and to the 5k functions. Yes, okay, good. Minus 6 over 5k minus 4. So really don't focus on these exponents, except to note that when k is 3, which is the case of circles, this recovers the old bound for circles. Okay. So what I hope to convince you of for this is that this new idea of how to cut algebraic curves into segments can yield some new incidence results, and maybe it can yield new results for you as well. And I want to draw a few pictures which suggest how this theorem of Schreier and myself works, where we can take n algebraic plane curves and cut them into n-to-the 3/2 segments. And really this idea is based on two previous ideas or observations. And one of them is a very nice theorem of Arnav and Schreier, where they're interested in a problem in R3 in eliminating what they call depth cycles, which I'll define a special case of for you in a few moments. So that's one piece. And another piece is a result of Ellenberg, Shalamoshi, and myself, where we take curves in the plane and we turn them into curves in R3 in such a way that this result of Schreier and Arnav can now say something interesting about them. So we'll say there is a transformation which takes R2 to R3, and it takes plane curves to space curves, and what it does is it takes what I'm going to call lenses, which I may not have defined if you're going to draw a picture, but these are essentially witnesses showing that a certain family of curves fails to be a set of segments. So a family of curves is a set of segments if each pair of curves intersect in almost one place. If you're going to find two curves that intersect in two places like this, these get mapped to what are called depth cycles. And so these are in three-dimensional space, so I'm going to sort of literally wave my arms. So you can imagine one curve is like this, and the other curve, so there's a distinguished direction, which is going to be the up direction. And so one curve passes below and above. The curves pass below and above each other in two different locations. So right where my right wrist is, my right hand is passing above my left arm, and where my left wrist is, my left arm is passing above my right one. So you're seeing this depth cycle. So I can draw a picture of it perhaps. So it's this curve is the curve I'm drawing right now is passing over this curve, passing under this curve. Maybe I'll draw it. So this one's going over, and here, this one's going over. So it's this picture here.
Is that somehow related to resolution of singularities?
So I'm not entirely sure, in part because it seems to me that this very much needs the fact that the reals are ordered field. And so that makes me nervous to say that there's a relationship. So I don't know. Yeah, it's an interesting thought, and I'm not sure.
I didn't want to make you nervous.
Pardon?
I didn't want to make you nervous.
Yeah, okay. I'm not aware of a direct relation, although I agree it does have that flavor to it. Okay. So we have this collection of n curves in the plane, and I'm trying to cut them to get rid of these lenses, right? These lenses are the things that are preventing my collection of curves from being a set of segments. And what I can do instead is I have this collection now of n curves in R3, and I can try to cut them so there's no depth segments. That ends up being an easier problem. Or rather, that ends up being a problem that was effectively solved by Arnault and Schreier. And they weren't interested in depth cycles for curves like this. They were actually interested in a slightly different problem, where you have families of lines, or perhaps line segments, and they defined a depth cycle to be a situation like this, where you have this line, and you have a line which passes above it, and then you have a line which passes above this one, but below this one. So it's 3, or perhaps more than 3, but 3 is the smallest example you can start to see this. And they were interested in cutting these lines into a smaller, or into as few segments, line segments as possible, so that all these depth cycles were disrupted. And now there was a complete ordering from front to back of these lines, which is an interesting problem in computer vision. So that was very neat. We realized the same idea could work here to eliminate these depth cycles, and this then tracks back into letting you get improved incidence bounds. So very briefly, how you might do this. So again, this idea of polynomial partitioning plays a role. So in what I drew before, we were in the plane, and we had a polynomial whose zero set partitioned the plane into a set of roughly d squared cells, where d was the degree of the polynomial, and there was n over d, so there was m over d squared points in each one. Now what we're going to do is we're going to partition R3 into regions. So I can draw a picture of a bunch of these. I'm not even going to draw these curves yet, but imagine they're there. And I'm going to partition R3, say this, into d cubed cells. So it's like polynomial p. Of degree d. So that R3 take away the zero set of p is a union of roughly d cubed cells. And again, if you were to look at these curves, a curve may enter several cells. But if I look inside of each one of these cells and ask how many curves are inside it, there's going to be at most the number of curves, which is n, over d squared curves per cell. And what this algorithm now does is it tries, so it's actually an algorithm which takes this collection of curves and cuts them to eliminate the depth cycles, and it works inductively. So if I only had, say, 1,000 curves, then I could cut it into 1,000 squared pairs just by cutting in a really inefficient way, but 1,000 is small, so that's fine. And then I can try to do things inductively, and I can look inside of each one of these cells and look at the curves inside of them, and try to cut those curves to eliminate all the depth cycles. And you can sort of see in your head, perhaps, I have d cubed cells, and inside of each one of them there's n over d squared curves inside of it. I can cut it into n to the 3 halves over d squared to the 3 halves. I can write it down. We'll see. Inside of each of the d cubed cells, we have n over d squared curves that can be cut into n over d squared to the 3/2 plus epsilon segments. So what's the total number of segments or the total number of cuts? Total number of cuts needed is d cubed. That's the number of cells times the number inside of each one of these. So this is n to the 3/2 d over d squared to the 3/2. So this is d to the minus 3 epsilon. These cancel. So this is n to the 3/2 times d to the minus 3 epsilon. So that looks sort of promising, right? We've looked inside of each one of these cells and we've cut the curve that live inside of that cell to eliminate all the depth cycles. But unfortunately, unlike with incidences, depth cycles are a very non-local thing, right? So with incidences, if a incidence occurs inside of a cell, the point has to be inside of that cell, the curve has to be inside of that cell, and you just look inside of the cell. But a depth cycle is this kind of weird thing where a curve could be way up here and another one could be way down there. They could live in very different cells, and yet they can still generate a depth cycle. And so this is only a small piece of the argument, but this is somehow the key piece which generates the great numerology of 3/2. There's other bits I won't get into which use a little bit of real algebraic geometry to be cutting the curves in other clever ways to eliminate all the depth cycles everywhere else. So that's an argument I just don't have time to describe. It's not, somehow it is the real meat of the argument, but if you want to understand the numerology, which sort of ultimately is how these things live or die, this is where these numbers come from. Okay, so to get back to this question, is 3/2 optimal? I don't know, but if you care about this problem of eliminating depth cycles arising not from, say, 2 curves, but potentially from 3 curves, so this algorithm eliminates all sorts of depth cycles. If you want to eliminate depth cycles coming from 3 curves, you really do need n to the 3/2 cuts, and that's because of the joint problem, where n to the 3/2 is the term exponent. And you can take a joints configuration with n to the 3/2 joints, perturb it slightly, and get something with n to the 3/2 depth cycles. So that's unavoidable. So I only have 10 minutes left, so I want to just say, or maybe less, maybe 5 minutes. How many minutes left do I have?
Well, up to 10, but maybe 5 would be good.
5 is better. So this is an idea which can be used to achieve better incidence bounds, and maybe can be used for other things as well, is my hope. And one of the reasons I've used this sort of revisionist proof of all these things to phrase it in the algebraic framework is that they work better in higher dimensions. And some of these arguments work in higher dimensions as well. And so I'll just state 1 or 2 theorems. So this is a recent one, which says if you have n curves, actually what I want to say, I'll be very concrete. Instead of talking about general curves, I'll talk about circles, just to make life easy. If you have n circles in R3, so they too can be cut into segments, right? So circles in R3 look like this, and it could be the case that a collection of circles is not a collection of segments. Certainly I can fix 2 points and have lots of circles in R3 that go through both of them. So I have a collection of circles in R3 and I want to cut it into segments. What I could do is I could project the whole thing to the plane and do my cutting there and move it back up, and that works. That gives me n to the 3/2 segments. But if I'm in R3 and the circles really are in some 3-dimensional configuration, you'd hope to do better. You can. So it's n circles in R3 and be cut into big O of n to the 4/3, which is better than 3/2, plus epsilon segments, provided the circles do not cluster into low-degree surfaces. So I mean, I have n circles in R3, they could all lie on a plane. I mean, there's nothing stopping that in theory from happening. And there's no way I can get a better bound than the planar bound if they're all on the plane. I mean, if I could, I'd have a better planar bound, which I don't have. So if they're truly in 3-dimensional space in a way which I'm going to be a bit vague about, then we can do better. Cluster into low-degree surfaces. And you can run some of these arguments that I was just describing a few minutes back. So I'm just going to quickly state a few results. So there's this beautiful theorem of Guth and Katz, which was an ingredient in their proof of the originating distance problem. And it's in some sense a version of Zimmer-Trotter, but for lines in R3. So they actually prove something more general than this. So this is a use cat as a special case. So they said, if you have m points and n lines in R3, and for the sake of argument, I will say not too many, they actually say something a little more intelligent than not too many in a common plane. Then the number of incidences between the points and the lines is at most, and now I'm going to write down a set of exponents which is better than the Zahl-Trotter bound. So it's m to the 1/2, n to the 3/4, plus m plus n. So they actually needed a slightly stronger statement than this to prove their distinct distance is small, but this follows from what they did. And again, it's not obvious that this is better than what Zahl-Trotter was, but take my word for it, it is, if not too many lines lie in a common plane. And in the same way as in the plane, you combine the Zahl-Trotter result with the cutting result, you can do that here as well. And so you can take n circles in R3, and you can cut them into n to the 4/3 of these segments, and then you can apply the same sort of result. So we can say, if we have m points and n circles in R3, not too many, in a common. So why were planes bad? Well, planes are surfaces where for any point you can have a lot of different lines all passing through that same point in the plane. For circles, that can still happen if you have a lot of circles in a common plane. It can also happen if you have a lot of circles in a common sphere. So those are now the two bad examples. So not too many in a common plane or sphere. Then the number of incidences is, again, it's the same thing. It's m to the 1/2, n to the 3/4, plus m, plus, and now instead of n, we're cutting into this many segments, and this is the bound that comes out. And in the same way you can use this to get better bounds for points and circles in the plane, you can use this to get better bounds for points and circles in R3, provided that not too many of them lie in a common plane or sphere. So that's maybe an interesting result, but you can use this to prove a result which is a bit cleaner and perhaps is sort of more obviously new, which is, and so Joseph mentioned this or was in response to a question right at the end of his talk, the unit distance problem in R3. So the question you could ask is given, I'd rather not use these n's, so I'm going to say x points in R3, how many pairs can have unit distance? Distance 1. And the conjecture is that it is at most n, or x rather, the 4/3. And it's certainly easy to obtain this many. You start with a configuration of points and lines in the plane that achieve the Zahl-Trotter exponent. You can turn it into this situation. So this is the conjecture. And until recently, the best known bound was big O of n to the 3/2. So this was due to, let's see, okay, I'm going to get the order of the names wrong, but Hanakova, Sharir, not Marx, Sharir, Matushek, and okay, well, it was a group of 4 people, about 2010, 2011 or so, and also due to a result of myself at roughly the same time. So we got this down. This is actually a very marginal improvement of what would have been known in the late 80s by Clarkson, Middlesbrough, and our previous career at Wetzel, using some classical techniques. And improving past this bound is a little bit tricky because there's examples of nice convex norms other than the unit distance norm, or other than the usual Euclidean norm where this really is sharp. And these are the norms where you just take a piece of a parabola and then take another upside down piece of a parabola and glue it together. And this looks like a pretty nice norm, and there really are n to the 3/2 distances. But using these ideas, you can improve it very slightly, and you can reduce this 3/2 by an epsilon. So you can say now it's big O n to the 3 halves minus 1 over 394. So it's a very small improvement, but it does get you below 3 halves, and somehow it's a delta. What's that? That's a delta, you said?
Yeah.
Oh, okay. Plus epsilon. Okay, so you lose an epsilon, you can't quite get 1 over 394, but you get very close to it. And very, very briefly, there's some transformations which turn this problem, so certain problem, number of unit distances for x points in R3 is really an incidence problem between points and unit circles in R3. You can turn this into a problem about points and unit spheres in R3. You turn this into a problem about points and circles in R3, and then you can apply these sorts of ideas, and you get a small improvement of what was previously done. Okay, so I'll finish.
We have time for some quick questions.
How does your proof distinguish between these norms and circles?
Yeah, pretty close. So it's what it better, right? So the key difference with these norms, I'll just say, if you take a circle in R3, and I tell you the circle came from intersecting 2 unit spheres, you can tell me what those 2 unit spheres were. And if I give you a parabola in R3 and I tell you that this parabola came from intersecting 2 translates of the unit parabola in R3, you can't figure out what those parabolas were. So there's a dimension count. There's degeneracy.
Earlier when you were talking about using polynomial to cut R cells, such that each of them has a number of points, what's the algorithm for that?
Yeah, so for some of these problems, there are algorithmic ways of doing it. For others, there's only existence proofs. So just to give some context, so this idea of using a polynomial was one of the major ideas developed by Cast to prove the distinction distance problem in the plane. So they did it in the original version for points. Given n points in Euclidean space, but I just said the plane, you can find a polynomial that will do this. And their method uses the Borsuk-Ulam theorem. If you want to do that computation, you can, but it's quite expensive. There was another idea developed by Matushik and Sharir and some others. I'm going to get that wrong, so I apologize. Another room, where you just take your collection of points and you randomly pick 2 of them and you draw a line between them. And then you randomly pick 2 on this side and draw a line between them. And then you randomly pick 1 in each of these, and you pick the lowest degree polynomial that goes through all 4. Now I've cut it into 8 sections. I pick 1 point in each of these, and I find the lowest degree polynomial that goes through all of those. And then I take the product of all those. And with high probability, this is going to do a good job in your partitioning. There was this other question, which is if you have lines in R3, how do you do a partitioning of those? So this is a later result due to Goof. And that one also uses something like Borsuk-Ulam. And nobody, as far as I'm aware, knows how to do that in an efficient way. And you could actually solve some very interesting problems in computational geometry, which all hinge on finding efficient ways to find that partition, if you don't know.
So efficient, you mean like linear time instead of quadratic, or
I mean-
polynomial instead of?
I mean, polynomial instead of, well, when I say exponential, it's exponential in what? So, if you want to find a perfect partition, that would be using Borsuk-Ulam, that would be exponential in the number of points, which is kind of heinous. If you want to find a epsilon good approximation, the naive way using Borsuk-Ulam is going to be exponential in 1 over epsilon, something of that nature. Whereas this method is genuinely polynomial in the number of points.
So in the case, you have points in algebraic curves in the plane, and they have the same number of each, so m equals n. Your bounds n to the 3 has plus the low 1, and you said in that case there's the lower bound still n to the 4/3 or something like this?
Yeah,
we
so
don't
that's
know
a
how
really
to-
ambitious conjecture. Yeah.
Uh-huh.
Yeah, so if the number of points is equal to the number of curves, n to the 3 halves is not at all impressive, because any 2 algebraic curves intersect at a bounded number of points, and that immediately gives you n to the 3 halves. So that's not interesting.
So it's only, the bound's interesting when m is much bigger than n, I guess?
When the number of points is very big compared to the number of curves, it's
Well,
good.
either way.
Yeah, and so the way you upgrade this argument is you partition in the parameter space, so that now what were used to be curves in the plane become points in some high-dimensional space. What used to be points in the plane become hypersurfaces in this high-dimensional space. And now when I do my partitioning in this high-dimensional space, inside of each cell there's 3 points, which correspond to curves, right? Because a lot of curves are already killing you, because it's curves to the power of 3 halves. So that's what's going on.
Cool. Okay, let's thank Josh again. And there's a reception upstairs.